All right, so in this lesson, we're going to be talking about solving by graphing, solving systems of equations by graphing. And so we're going to first figure out what are systems, and then what do solutions to systems look like, and how can we find those solutions by graphing them. So let's go ahead and get started. If you're watching this video, you might want to click on the PowerPoint that is in this Canvas assignment. This is just a kind of a fun video that I thought you might enjoy, since our first example is on roller coasters. So you might want to go to the PowerPoint and watch that video. It'd be kind of fun. Anyway, let's move on to this problem. Let's say we have two different amusement parks. One is called Coaster Paradise, and the cost to get in is $2, and then it's $2 per ride. And so we would want to write an equation for the cost of going to Coaster Paradise depending on how many rides you go on. And so that equation is going to look something like this. We're going to have $2 for each ride, that's our slope, plus just to get in the door, it's going to cost you $2. And so that's going to be our linear equation for Coaster Paradise. Fun Spot Park, on the other hand, costs $6 to get in, and it's only $1 per ride. So that equation is going to look more like this. It's $6 to get in and $1 per ride. That's the slope. So it's 1x, or just x, plus $6 to start off with. And so here we have our two equations, y equals 2x plus 2 and y equals 1x plus 6. And what we want to do is we want to figure out how many rides will the cost at both parks be the same price. And so if we can just kind of figure out what's going on here, we have two graphs here. Maybe I should make this go up here. I'll just put it here and erase this one. We have two things going on here at the same time. At Coaster Paradise, if I'm going to graph this, let's say I graph this in green here. At Coaster Paradise, we're going to start at $2 to get in the door. And then every ride we go on is going to cost $2 more. And so the graph is going to look something like this for Coaster Paradise. Then if we go to Fun Spot Park, I'm going to graph that in blue. This starts at $1, $2, $3, $4, $5, $6 to get in the door. But then every ride we go on, it costs us an extra $1. And so if I continue that, it's going to look something like this. And so all these points that are blue make this equation happy. All the points that are green make this equation happy. And so there's one point here that makes both equations happy, and that's this point right here. That happens to be the point 1, 2, 3, 4, and up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the point 4, 10. So here's what that means. If you go to Coaster Paradise and you go on 4 rides, it's going to cost you $10. If you go to Fun Spot Park and you go on 4 rides, it's also going to cost you $10. And so how many rides will the cost at both parks be the same? Well, that's 4 rides. And we can check to make sure that's right, because if I plug a 4 in here for this equation at Coaster Paradise, 2 times 4 is 8, and 8 plus 2 is equal to $10. If I plug 4 in here to this equation for Fun Spot Park, then it's going to be 4 plus 6, and 4 plus 6 is also $10. So in other words, this point makes both equations true. That's the solution to the system, and the system is both of these equations, and we want to find a point that makes both equations happy, and that would be the solution to the system. Let's see what this looks like when we talk about solutions to systems. A solution to a system is the point that makes both equations true. And so you want to make sure you put that in your notes. A system of equations is more than one equation. And most of the things that we're going to do, a system is going to be 2 equations, and we're going to find one point that makes both of the equations true equations. All right, so let's just do this example. Is this, the point 2, 5, a solution to this system? So here we have a system just like we had with the amusement parks. And what we want to do is see if this point makes both equations true. So I'm going to plug this point into this equation first. We have y, but y is 5, and that equals 3 times x, but x is 2. Here's our y value, and here's our x value, minus 1. So is that a true statement? Well, we know that 3 times 2 is 6, and 6 minus 1 is 5. And so it does make this equation happy, okay, or true. And so does it make the other equation true? So in the other equation is 4 times x. Well, our x value is 2. Well, that's going to be 4 times 2 minus 2 times y, and our y value is 5. Is that going to give us a value of negative 2? Well, we know that 4, that's a 4, times 2 is 8. 8 minus 2 times 5, that's 10. And 8 minus 10 does give us negative 2. So it does make this equation happy. And so is this a function to the following system? And the answer to that question would be yes, because it makes both equations true. Let's take a look at this situation, example number 2. We want to check to see if this is a solution to the following system. And so if I plug it into the first equation here, I know that y is my 1. So 1 equals, and we're going to have 4 times x, and x is the negative 3 minus 11. So is that a true statement? Well, we're going to have 4 times negative 3 is negative 12. Negative 12 minus 11, that's the same thing as negative 12 plus negative 11. Well, that's negative 23. That's not 1. So it doesn't make this equation true. And so we don't even need to check the other one. It doesn't make this equation true, so it's not going to make both equations true. So the answer here is no. The point negative 3, 1 doesn't make this system, is not a solution to this system. Let's take a look at this example. We want to find the solution here. There's only one point that makes, for most situations, that makes this system a solution to the system, that makes both equations true. And so what we want to do is figure out what are the points first that make this equation true. And so that's all the points that are on the graph. And so I would start, if I were to graph this equation, at 8, which is right here, and the slope is negative 2. Well, that's down 2 over 1. Down 2 over 1. And I can continue going down. Down 2 and over 1 would be here and here. I'm all over the place here and here. And so I can continue to find all those points. I can even go up 2 and left 1. But all of these points here make this equation happy. So there's a lot of them that make the first equation true. Then there's going to be some points that make the second equation true, but we want to figure out what those points are. And that's all the points that are on its graph. So we're going to start at the y-intercept, which is negative 1. And then here the slope is positive 1. So we're going to go up 1 and over 1, up 1 and over 1. And we're going to continue to do that. Okay, and I can even go down 1 and left 1. But all of these points here make the second equation true. But there's only one point that makes both equations true. And that particular point is right here. And so that's the point when x is 3 and y is 2. So the solution is 3, 2. And we can check to make sure that it is the solution by plugging the point 3, 2 into both equations. If I plug the x in here, negative 2 times 3 is negative 6. Negative 6 plus 8 is 2. So it makes this equation true. And if I plug it into here, 1 times 3 is 3, and 3 minus 1 is 2. It makes both equations true. So the solution is where the 2 points intersect. Let's try the same thing with this equation. We know here, if I were to graph this one, it starts at 3, the top one, and the slope is 2, up 2 over 1, 2 over 1. And I could go down 2 and over 1 as well, but all of these points make the first equation true. Then, if I want to graph the second equation is going to be and it's in standard form right now, and so there's two ways I can do it. I'm going to do it by plugging in zeros. I could also get the y by itself. But if I let x be 0, then if I let x be 0, then this would be gone, and -4 times -2 would give me 8. Well, that's the point 0, -2, which is right here. If I let y be 0, then this would be gone, and I would have 2 times 4 would give me 8. Well, that's the point 40, which is right here. And so looks like that's up 2 and over 4. I can also go down 2 and left 4, which would be here. And we would have where these 2 points intersect, which is this point right here. Now, this is going to be a hard one for us to define because it's kind of between two things. But it would have one solution, and that's where those two lines would intersect. Let's go ahead and look at this next situation. It says, Mr. Panning will give you a candy bar right now if you can find the solution to the following system. And so this is a different kind of situation that happens. The first problem is going to be where it's going to cross at 4. That's the y-intercept, and the slope is 2. So we're going to go up 2 and over 1, or down 2 and left 1. And all of these points are going to be on the graph. Then if I graph the second equation, this time I'm going to do it by getting the y by itself. I'm going to subtract 6x from both sides. So I will have -3y equals -6x plus 9. And if I divide both sides by -3, that'll be y equals -6 divided by -3 is 2x minus 3. So this one's going to start at -3, but its slope is also 2. And so these lines are going to be parallel, which means, are they ever going to intersect? They're never going to intersect. All of these points on this line make this equation happy, and all the points on this line make the second equation happy, but there isn't going to be a point that makes both of them happy. So that means we're not going to have a solution to this system. So there's no solutions if the lines are parallel. So sometimes we don't have a solution. Now, sometimes we have an infinite number of solutions. If the two lines are right on top of each other, then there's going to be an infinite number of solutions. So there are an infinite number of solutions if the lines are the same, which happens occasionally. And then there's one solutions if the lines intersect. And this is what's going to happen most of the time. They're going to intersect and they're going to have one solution. So that is the PowerPoint and the notes for this assignment. You can go ahead and work on your assignment, and we will go over questions that you have tomorrow.